Well, today we're going to solve some logarithmic and exponential equations. And we're going to try to do some simple examples that don't require sophisticated log properties. So this is just the basics. There'll be a follow-up video where we will address the more interesting equations. Stay tuned. So an exponential equation is one where you not only have an exponent, a power, with a base and an exponent, but the exponent has a variable in it. The simplest type of exponential equation to solve is one where you have a power equal to a power, and both of these powers have the same base. In this case, it's base 5. Well, if the powers are equal and the bases are equal, then the exponents have to be equal. That is, 3x plus 5 must equal 7x plus 1. And now it's straightforward, linear algebra. You're going to subtract 3x from both sides. That's going to get 5 equals 4x plus 1. You're going to subtract 1 from both sides. And you'll have 4 equals 4x. Divide by 4. And the answer is 1 equals x, or x equals 1. Pretty easy. Not much different about the second problem. It has a base of e, but there's two equal powers that have equal bases. So you're going to go ahead and say, yeah, then the exponents have to be equal. So negative 12 equals x times x plus 8. And I'm going to distribute the x through here. And as soon as you do that, you'll notice that x squared appears. Well, in equations with x squared or x cubed, higher powers of x, you want to get things equal to 0 and then try factoring. So I will add 12 to both sides like this. And on the left I have 0, and on the right I have x squared plus 8x plus 12. You'll want to factor that into the product of these two binomials. I think x plus 2, x plus 6 are appropriate. Why 2 and 6? Because 2 times 6 is 12, but 2 plus 6 is 8. So I have videos on that if you're interested. In fact, I think I put one out today. But you solve this by looking for numbers that cause 0 over here, such as a negative 2 right there. Negative 2 plus 2 is 0. Negative 2 plus 6 is 4. 0 times 4 is 0. Another solution comes from here, and it's negative 6. So the solutions are negative 2 and negative 6. Here's another problem where I have equal powers, but I don't have equal bases. Base 3 here, base 81 there. This is where it's helpful to know that 81 is just a power of 3. As a matter of fact, 81 is 3 to the 4th power. 3 times 3 times 3 times 3 is 81. So I'm going to rewrite the right side of this equation as 3 to the 4th raised to the 2 power. Then I'm going to take these exponents and multiply them together. And now I have equal powers with equal bases. So, of course, that means the exponents are equal. So 4x equals 8. Divide both sides by 4. X equals 2 is the answer to this problem. Problem 4 requires something similar, but you have to do it actually on both sides. Both of these powers have bases that have something to do with 5. 25, for example, is 5 squared, 5 times 5. And on the right, hopefully you recognize 1/5 as 5 to the negative 1 power. So just like in the previous problem, if I multiply these exponents together, I get 5 raised to the 6x plus 2 on the left, and on the right I get 5 to the negative 4 power. Okay, now I have equal powers with equal bases. That means the exponents are equal, so I set those equal. 6x plus 2 equals negative 4. Subtract 2 from both sides. 6x is negative 6, and divide by 6 to arrive at the answer, negative 1. And you can pause and rewind these, whatever you want to do. Trying to keep the video short. Believe it or not, both of these are powers of 2. Yeah, 2 times 2 times 2 times 2 is 16, so this is 2 to the 4th. This is a big power of 2. Multiply enough 2's together, you'll arrive at 128. In fact, it requires 7. 2 to the 7th is 128. Okay, multiply these exponents. multiply these exponents, and I'm going to go ahead and distribute while I'm at it. So I'll have 7y minus 70. Now we have equal powers with equal bases. You can set these equal and then just do some simple solving of a linear equation. I'm going to subtract 7y on both sides. So subtract 7y, subtract 7y. You've got 5y equals negative 70. And then all you have to do is divide both sides by 5. And you're going to get y equals negative 14. Okay, this one's going to slow us down because I don't have a power equal to a power. This is actually going to take a log property unless you have a base 5 logarithm function on your calculator. And I'm going to assume you don't. So my calculator has 2 log buttons. It's got the natural log and it's got the common log. And you're just going to pick one of those. So I'll go with common log. Common log of 5 to the 3x power. Common log of 41. Just take a log on both sides. You would want to do this anytime you're solving something that has a variable up here, but no similar power on the right. Then you're going to use the property you saw in a previous video where you can take this 3x, pull it down front. I have a video called Properties of Logarithms. This does look a little abstract the first time you see it. But the goal is to know what x is. X is over here with a factor of 3 and a factor of log 5. So if you just divide both sides by 3 and by log 5, they will vanish off the left side. They will emerge as divisors on the right side. And after canceling 3 divided by 3 and log 5 divided by log 5, you come up with x equals this. And that doesn't look very nice, so we're going to turn it into a decimal now. And we're going to do that by going log 41 divided by 3 divided by log 5. You got to divide by both of those. And the decimal you get for that is about 0.769, approximately. By the way, it would have worked exactly the same had we used the natural log on both sides here. In fact, that's kind of neat to watch. So let's go redo this calculation using natural log. So it's natural log 41 divided by 3 divided by the natural log of 5. Same answer. Okay, so here's a problem where you have to solve for x up in the exponent of a power that's based on e, a natural exponential. Start by trying to isolate e to the 5x. So we're going to add 8 to both sides. We have 4e to the 5x equals 28. Divide both sides by 4. And now you have e to the 5x equals 7. Now this problem was built for the natural log. Why? Because if you take natural log of e to the 5x, you are doing inverse operations. The base e exponential and the natural log are both based on e and their inverses, so they cancel. So now you have 5x equals natural log 7. And now divide both sides by 5 and you're done. So I would prefer, if you were my student, that you leave the answer like that. Somebody else might say convert that to a decimal. Easy enough. Natural log of 7 divided by 5 is 0.389. This problem, on the other hand, is built for common logs. Why would I say that? Because there's a power with a base of 10. And the common log is a log that has its base of 10. So take a common log on both sides. And remember that common log is a base 10 log A base 10 log and a base 10 exponential are inverses. That's the reason I did that in the first place. On the left, I get 2x. On the right, I get something I can do on my calculator. However, this is just a power of 10. This is 10 to the 5th power, so the common log of 100,000 is 5. Now divide by 2, and you get x equals 5/2, or 2.5. We have a few more problems, so stick around. Now this problem has logarithms on both sides, and they're both base 5 logs. And these base 5 logs are equal. So it stands to reason that the contents or the arguments of these logs should be equal. So this problem, we just start off by saying 12 equals 2x minus 8. It's that easy. Add 8 to both sides. You get 20 equals 2x. Divide both sides by 2, and 10 equals x is the answer to that problem. This one has common logs. Not base 5, but base 10 logs. And they're equal, so that means what's inside of them is equal. So 80 equals x squared minus 1. I've got x squared here, but I don't think I need to get 0 because there's no linear term. I think the easiest thing to do with this problem is to add 1 to both sides. 81 equals x squared. Take the square root of both sides, and don't forget that the square root of 81 is 9. Also don't forget that not only is 9 times 9 81, but negative 9 times negative 9 is 81. And so you should write your answer as a plus or a minus. And you have to watch out that sometimes you'll get an answer that doesn't really plug back in here. But I can promise you both of these work. But occasionally you'll get an answer that when you plug in here, it'll compute to a negative number. We don't want those answers. We discard them because we're not going to take logs of things that are negative. Okay, there are two ways to solve this, and I think I'll do them both. First of all, remember the base 5 log of something is the number that you can put up here to make what's inside the log. What number can I put up here? This number. This is a logarithm. Logarithms are exponents. So 5 to the 3rd power is 2 plus x. That means 125 equals 2 plus x. Subtract 2 from both sides, and you are done promptly. But I mentioned there was another way you could do this. You could use inverse properties of logarithms and exponentials. The inverse of a base 5 log is a base 5 exponential. So you could quite literally go to both sides of this equation and use what you see as an exponent sitting above a 5. You do it on the left and you do it on the right. You do that because base 5 exponentials and base 5 logs are inverses. And then you see that we're in the same situation we were with this approach. These approaches really aren't any different. And you get an answer of 123. Okay, I think I'll solve this one just one way. Most of my students like to use the definition of logarithm and say, okay, that's a log. That means it's an exponent. It likes to sit on a base. The base it sits on is 2. So 2 to the 3rd power equals x squared plus 2x. The contents or the argument of the logarithm. So 8 equals x squared plus 2x. Now this time I think I will get things to get to equal to 0 by subtracting 8 on both sides. So I have 0 equals x squared plus 2x minus 8. I'm going to factor that as a product of two binomials, and they look like x and plus 4 and minus 2. Those factors reveal roots or zeros of negative 4 here and positive 2 there. And those are the solutions to problem 12. So we have x equals negative 4 and x equals 2. Okay, here's a problem where we have a natural log on the left. Now, if you want to use the definition of logarithm to solve this, you could go like this. You could say, remember, a natural log is a base e log. And I have the value for the logarithm. I have the exponent. I have the exponent that likes to sit on this base to make the argument of the logarithm. So this exponent on that base gives you the answer to the power which is what's inside the logarithm. Divide by 2 and you're done. So e to the negative 3 over 2 is equal to x. I think a nicer way to write that, though, without negative exponents is 1 over 2e cubed is x. That's what the negative exponent does to the e there. It says I want my e factors to be divisors, not multipliers. Now, I mentioned there's another way to start this problem. What's the inverse of a natural log? Well, that's the base e exponential. So you can do the problem like this. And I think this technique is good to know. In this problem, it doesn't matter that much. But since these are equal, they can act as exponents to sit above base e, or any base you want, to make equal powers. I chose base e because of the inverse property of the base e exponential and the natural logarithm. And you will notice that we're exactly in the same spot we were with the other problem, or the other approach. So I'm not going to continue that. So on problem 14, I think I will use this inverse approach. You've got something inside of a natural log, like x squared, and you're trying to get out of the log. Use the log as an exponent above the e, but you got to do it to both sides like this. Okay, I did that because these are inverses, so now I have x squared equals e to the 10th. Take the square root of both sides, and you get x equals plus or minus the square root of e to the 10th. But the square root of e to the 10th is the half power of e to the 10th, which is just e to the 5th. So my best answer for this one is x equals plus or minus e to the 5th. And of course, that's two answers written to look like one. That's it for this video. I hope you enjoyed it. My name's Eric. Have a good day.